Good afternoon, everyone. My name is Kenny. I'm from the University of São Paulo in Brazil. Today I'm going to present my paper entitled Commercial MAV Velocity Estimation using Gaussian Process Regression for Drift Reduction. This is the outline of the presentation. And first, let's have a brief introduction about the topic. So today we can see many applications using microwave vehicles or MAVs. For example, we can see applications involving agriculture, surveillance, and package delivery. So probably in a few years, you're going to see a lot of drones delivering our packages to your home. In terms of commercial MAVs, they have the advantage in comparison to custom build because they have out-of-the-box autonomy. So you can go to a store, buy a drone, and it's already good to go. You have fast replacement. So if you damage one of your robots, you can easily replace it for another one. And it's going to operate pretty much the same as the previous one. And you also have extensive documentation. Since anyone in the world can buy the same drone as you, probably going to find a lot of documentation online, in photos, in many other platforms. So it's really helpful in that terms. However, if you go for autonomous applications using this platform, usually they rely in inertial measurements for an IMU to get position and velocity. And IMU suffer from drift over time, which is not good for this kind of applications. Usually these MAVs also have optical flow and GPS as an additional sensor, but they also might fail under visual or signal obstruction. So again, it's going to only rely on the IMU measurements and it's going to drift after some time. So a solution for these problems is to use sensor fusion methods. We have filtering-based techniques like Kalman filters and particle filters, but they require calibration and parameter tuning. So if you don't have access to raw sensor measurements or any other specifications, it's going to be very hard to calibrate these parameters. And nowadays, we can also find machine learning techniques for these problems. And in this work, we chose to work with the Gaussian Process Regression model, that's going to call here GPR. And the reason we did that is because the GPR model works really well with OR Inoue data, which is our case for this problem, and it's a non-parametric kernel-based method. So I'm going to explain a little bit later what is the kernel-based that we're using. And the solution is based, okay, so we have odometry coming from our MAV, which outputs for us poor odometry data, but we can also rely on that for our initial estimation. And we can add an additional IMU to compensate for these errors. So based on that, and on the GPR model, we can improve the localization system accuracy. And the contributions of this work, so we can train a GPR model for this drift reduced velocity estimation. We access 3 different kernel models and the training preparation for this regression test. And we evaluated our method in 2 real-flight datasets. Here's the system overview. So in this work, we are using the commercial available MAV from Terra, the MIBOC2. It has a full HD camera, 5 Hz odometry system. So in this platform, we don't have access to the raw sensor measurements. It only outputs for us velocity and position or orientation, but we don't know exactly how the fusion of these sensors are happening. So we can't know exactly how the parameters are calibrated. We also have GPS, and we also have Wi-Fi communication to enable communication with a computer or another onboard computer. And to illustrate the problem we were having, so if you want, we capture the motion of this MAV inside a lab with a Vicon tracking system, and we could notice that even if the MAV was pretty much doing a circular trajectory, the odometry system believed it was going into the x-axis as well, which was not very good for our application. So the modification that we did was we developed a 3D printed platform that we position on top of the MAV here, and we added an additional IMU. We have a Raspberry Pi 4 to control the system and also to estimate using the velocity using the GPR model. The Raspberry Pi 4 is using the robot operating system, ROS Connect, and also it's running Ubuntu 16, and it's communicating with the MAV using Wi-Fi. And here's a basic overview of the system. So we have an outputting acceleration data at 100 Hertz. We have a pre-processing step to reduce noise. And we also have the bebop2 outputting velocity at 5 Hertz. All this data comes into our GPR model, and we have the BGP with our velocity with drift reduction. So just to give basics of the GPR model, so we first define our training set of data. So we have D, it's composed of X matrix of D-dimensional inputs, and Y, it's a matrix of O-dimensional training set, which in our case is going to be the velocities for X and Y. And when we are working with GPR model, we basically are trying to estimate our predicted distribution over this multi-output training set based on the mean given by equation 1 and the variance given by equation 2. And the key element of the GPR model is the kernel function or covariance function given by the function k here. This is gonna give us for us how the input corresponds to the output data. So depending on the kernel method you're using, you're gonna have a better or worse estimation. So it needs to be carefully chosen for this application. So here we selected 3 kernels. These kernels were selected based because they work better in case of dynamic systems. They can be differentiable if you want to. So we have the square explanation given by equation 3, the Mathern 3 given by equation 4, and the Mathern 5. The parameters R and L are given by these equations here, which is also, in case of the L function, is also our hyperparameters, the length scale that we want to estimate to improve, optimize during the training step. And also we want to retain the signal variance, sigma f. So to summarize our training steps, so we first define our training data, which for our application is going to be acceleration and the velocity coming from the odometry system. And we're going to output the drift reduced velocity, VGT. To match the data size, since we are operating at different frequencies, we interpolate the data coming from the odometry system to match the size of the acceleration data from the MU. We concentrate our data points in higher velocities, whereas our search is going to be higher. So whenever you are operating at low speeds for our training data set, we only consider a few data points because the GPR model complexity scales with the amount of data points you're training. So we don't want to overcompensate for it when we have low uncertainty. So the results that we got with this application, let's explore. We have 2 flight data sets. The first, we only consider mostly straight lines, so more like rectangular trajectory. And the second, we consider more challenging trajectory, more curvy with higher velocities. The tracking, vital motion track system was used for ground truth data. So also for the training set and also for evaluation. And to obtain velocity, we use it, since we only have position using the system, we use it a common filter. Analysis of the results were made in terms of trajectory tracking. So we integrated these estimated velocities afterwards to obtain position. And we also compare our results with the monocular version of a visual slam algorithm called Orbslam, and also with the own MAV odometry as well. So here we have our results for these 2 trajectories in terms of data set 1 and data set 2. As we can see here, we could improve by around 34% our results in terms of its own odometry using the GPR model with Mathern 3 kernel for the 2 data sets. And here you can see the results for the velocity estimation. So when we are reaching 1 meter per second in the two axes for Vx and Vy, you can see that the solid line is the ground truth and the green line is the odometry system. So we can see that we have a great favor here when it's reaching higher velocity, but the GPR model is able to maintain within an acceptable bound. And for the second data set, the same thing happens, but you can see a greater error here because the velocity is a little bit higher than the previous one. So to conclude our work, based on the obtained results, we could reduce the drift of velocity estimation in this kind of application for commercial MAVs. Our method does not require parameter tuning or calibration. So if you have a good data set and we can put our 2D platform on the top of the map, we can improve our localization system. And we could prove that we could outperform the native odometer system and a visual algorithm for navigation purposes. That's it. Thank you.